What does a lazy river and a Greek mathematician have in common? We're going to be learning about buoyancy today. Hopefully you've been joining us along our little physics tour. The last video we talked about pressure. We talked about atmospheric pressure, we talked about water pressure. They all have to do with fluids. And if you remember, anything that's submersed or surrounded by a fluid has pressure on it. So if I'm walking down the street, we said, hey, the entire atmosphere is surrounding you. And that's right, your body has pressure on it from every single side because of those gas molecules. If I'm swimming, right, whether I'm completely submerged, right, that water is exerting pressure on my body from every which angle. And that's important today because we're talking about buoyancy. Now buoyancy, the origin of the word is either Spanish or French, meaning to float. So a lot of times when we think about buoyancy, we think, hey, do things float or do they sink? Now buoyancy is a force. That's right, so if I'm swimming in a fluid, say I'm swimming in water, that fluid is pressing on all my sides. Now what we're really concerned about is that force that's pressing on the bottom of us, that's pressing us upward. Now we know that gravity is pulling us down and that buoyant force is pressing us up, right? It doesn't take too much to know that, hey, if we're looking at the net force, we're saying, hey, overall, if the force pulling us down is greater than the force pushing us up, we're going to sink. If the force pressing up on us is greater than the force pulling us down, we're going to float. And that's exactly right. So let's take a look at a couple examples. Our first example, right, we have a picture of a boat. So how do we know that that boat floats? Is we have a buoyant force on the bottom that's pressing more than the pulling force of gravity. So that's right, we have a bunch of arrows here on the bottom of our boat. The next one, we have surfboards, right? If you love surfing, think about it. You change the board, right? If I'm a little bit larger, I'm gonna get a board that's a little bit bigger because it can hold my weight. What we're saying is that increases the buoyant force on the bottom of the surfboard. If I wanna have more buoyant force, I need to have somewhat of a larger surfboard. Now, you might have been that child that really struggled with swimming, or maybe you still don't know how to swim, okay? And you might remember going to the pool and you put on floaties on your arms, right? That force, buoyant force, right, is pressing on your arms, is pressing on the floaties, and that's keeping you afloat. Okay, another example is a buoy. That's right, if you look, it's very similar to the word buoyancy, right? Buoy, the whole idea is that these are markers that float in the water. Right, and they give a lot of information. They might tell you if you're going north or south, or you're going out to sea or coming back. They might have different numbers on for different channels. So just kind of going back to it, the buoyant force is what's keeping these buoys up. And that way they're resting in the water, they're floating in the water. In the last example here that I want to make sure I mention, right, picture a nice blimp, right? This large ship that's filled with air that's lighter than the air around it. And what's happening is, with a combination of fans and jets, right, it's actually rising or it's staying lifted in the air, and that actually has to do with buoyancy as well. So don't just think of water, don't just think of liquids, right? We're talking about all fluids exert a pressure. In this case, that pressure, that buoyant force is pressing up rather than having gravity just pull it down. Now, if you were in my class, the next assignment we would do is we'd have a foil boat challenge. What we would do is we'd take a piece of aluminum foil, they'd all be the same size, everybody would get one, and your job would be to design a boat out of aluminum foil, just aluminum foil, that can hold the most amount of pennies before it sinks. The goal here is we want it to float the best. So how do we do that? What design works, right? Maybe you have some experience thinking back. Maybe you took a swimming class and they talked about, hey, how do you float? So rather than just swimming, how do you float and kind of survive? If you're, I don't know, shipwrecked somewhere and you needed to keep afloat, right, what would you do? A lot of times they'd say, hey, take a nice giant breath of air, hold in your lungs, your body's going to be floating better. Now why? So I'm not going to give away the answer quite yet on how to do the foil boat challenge, but what I will talk about is Archimedes Principle. This is that Greek mathematician we talked about. So if we went back to the history books, right, there was a king basically of Sicily at the time, right, and he became king and he wanted to be well known. And so what he did was he hired a blacksmith, right, and he said, hey, here's a set amount of gold and I want you to make a crown for me. Which is awesome, right? So the blacksmith worked on it, he gave the crown back to the king. Now the king had a dilemma. he wasn't sure that the crown was made out of 100% gold. What if the blacksmith, right, he tried adding some other materials in it and then he kept some of the gold for himself? So he had this question and he went to Archimedes. Now the story goes, and this is kind of where it turns into more myth than anything, right? The story goes he was sitting in his bathtub when he came up with the idea how to prove the crown was made out of 100% gold. And he was in the bathtub, so what did he do? He leapt up, he yelled Eureka, which basically means aha, I got it, and he went running through the town square. Now that's a scary sight to think about. And again, a lot of that is probably more myth than anything else, but it makes a great story. So let's go back to Archimedes. What was this principle? What did he come up with? This is the idea. If you submerge or place something in water, the water level is going to rise, or it's going to displace water. The amount of water that rises or is displaced, that is going to be actually equal to the buoyant force. Now that sounds kind of crazy, so let me kind of show you an example here. Now I have a cup filled with water, okay, and you can do this kind of at home. So it's filled to the brim, right? No more water can fit in here. Matter of fact, I gotta be careful so I don't spill any here. And I'm gonna have a container underneath. Now it's gonna be empty, there's no water in there. I want to capture, if I put an object in that glass of water, I want to capture any excess or any displaced water. So, courtesy of McDonald's back in the day, right, I had this little car here. If I place it in the cup, you notice that as soon as I place it in there, there's water that's pouring over their edges. This is the displaced water. Now, if I were to take the displaced water here, right, if I were to take this water that's kind of in this extra cup and I were to weigh it on a scale, right, I'm going to have something probably in grams. The grams of water I have in this overflow cup is equal to the buoyant force on the bottom of the car, right? Now think about it. If the buoyant force is less than the weight of gravity pulling on it, it's going to sink. But if I have a lot more water, that this weighs more than the actual object I'm putting in the water, it's going to float. So Archimedes is saying, hey, any of the water that's in the overflow cup, right, is equal to the buoyant force. And if that buoyant force is greater than the force of gravity, then it's going to float. If the buoyant force is less than gravity, right, then it's going to sink. So that's a pretty neat, little interesting kind of principle that we go back to. So it's also kind of thought about like the law of buoyancy or Archimedes Principle. Now, if you're thinking this through, you may have learned about density. Basically, how close particles are in an object. Basically, we want to say, hey, something that is more dense than water is going to sink, right? So take, for example, this car, right? If I look at the overall density, so I measure the volume of it, and I measure basically how packed the particles are, okay, I can find the density. If the density is greater than 1 gram per centimeter cubed, then it's going to sink. If the density is less than 1 gram per centimeter cubed, right, it's going to float. So there's a kind of other way to go about this. You can find the density of it and, you know, the whole 9 yards, or you can kind of go back to this idea if I place it in a cup. Okay, to show you another example here, say I take that glass, it's full of water again, okay, and I have an object that I know is going to float, or I'm not really sure yet, right, and I place it in there, and I'm going to place a container underneath to capture that overflowing water. So here I have it's basically just a little Nerf dart for my little Nerf guns. If I place it on top, okay, it automatically starts to float. Now, how do I find, so if something's floating, how do I find the amount of buoyant force? I know it's greater than the gravity, okay, that makes sense now, but how do I find the buoyant force? Maybe that's my job. If I submerge the dart completely in water, okay, it's going to move water. It's going to displace some water. Again, I would take that extra water, I'd measure it on a scale, and I can actually prove what the buoyancy is. Now that we have a better understanding of kind of Archimedes' principle and buoyancy, how do we apply this to maybe something that you might do or maybe something that I would do? So let's go back to our surfing example. Maybe as a child you had a boogie board, right, or a body board, And what you did, you went out to the ocean, you're like, hey, this is easy, I'm kind of floating a little bit on it, what if I stand on it? And what usually happens is the board sinks underneath the water. And why? It's because the force, or the weight of your body and the board, is greater than the buoyant force. So as you kind of progress into surfing, what do they end up doing? If you look at a surfboard versus bodyboard, the surfboard is not only longer, it's also wider. And what that does, right, my body and that board combined, the density is less, right, than the water. So what happens is the buoyant force is greater. Right, if I want to increase that buoyant force even more, so say maybe I get larger and I get kind of taller and maybe a little bit more weight, right? If the board gets longer and wider, overall it's going to have a greater buoyant force. Matter of fact, you can actually take a look at YouTube. I'll put a link down below. There's a board that set the Guinness World Record for the most amount of people. And think about it, it would have to be really large to accommodate a greater amount of people on it. You need a really large buoyant force. Hopefully this also brings up your answer for that foil boat. Okay, what was the best design? Okay, I've done this for years and years. Okay, the best design is one that you cover the most surface area, right? So you want to use the aluminum foil to the greatest extent you can with really low edges. And what that does is it allows you to take up the most space when it starts to kind of drop a little bit due to the weight of the pennies. Right, if you folded that foil over top of each other, right, it's going to create a smaller area and it's actually going to be more compact. So we want to be able to take up the most space. Now think about a cargo ship. This maybe will help you kind of understand it, right? If we look at the hull of the ship, okay, why aren't they flat, right? We also want to do something else. Not only do we want to have something that can hold a lot of weight, we want to displace the most amount of water. Think about it. The more water we displace when we put the boat in the water, right, the greater the buoyant force. Now, boats are made out of steel, so if it was completely solid steel, it would just sink. So if we look at the hull, it's empty in the middle. There's a lot of empty space, and that's on purpose, because even though steel's dense, the overall density of the boat is very, very little. It's less than the density of water. Right? So that empty space is what keeps that boat floating. It displaces a lot of water, but it's also hollow. Right? So now we can stack up a lot more weight. The design also has to go back to thinking about, hey, it's going through the ocean, so it needs to be able to take waves, it needs to be more stable. If you were looking at more of a design of, say, maybe a barge going through a river, right, it's not going to face as many difficulties, as much extreme weather, so they're going to be a little bit more flat on the bottom of the boat. So let's go back to Archimedes and the crown. How did he use his own principle to figure out if that crown was made out of gold? Now he knows how much gold the king gave the blacksmith. We'll say it was, 1,000 grams or 1 kilogram of gold. Right? So he took 1 kilogram of gold and he placed it in water and he watched the displacement. He knew exactly how much water it displaced. So if the crown was made out of a mixture, say it was made out of silver, it was made out of something else, and it weighed 1 kilogram, but it displaced a different amount of water, he knew for a fact that it was made out of a different material and that not all the gold was used. Right? The story goes that the crown actually was not made out of pure gold, or that the blacksmith took some of it, so therefore we know the fate of the blacksmith. I hope this video kind of helped you understand Archimedes and buoyancy and why things float. There's an awesome link down below to talk about a TED Talk. Maybe Archimedes, the whole story was wrong. Maybe instead of a crown, it was a large vessel that was given as a gift. So take a look at that video. I also post a couple other links down below to help you understand these concepts. Thanks for watching. I hope you have a good day.